Hi, my name is Ayden, and we will be talking about principles of flight. First things first, why are we talking about principles of flight? Well, you want to know more about principles of flight because our goal is to develop an understanding of how the aircraft behaves in flight. It'll make you a better pilot. These are some of the resources that we were using. And to kick things off, I'm kind of talking about how water behaves. Water is a fluid. The point I'm trying to make is that air is a fluid. So air behaves kind of how water does when you have your hand in a pool and you push it really fast. You remember, like there's like a gap right behind your hand when you push it where the water needs to fill in, and the water accelerates to try to fill in that hole that your hand left behind. Air does this too, like an 18-wheeler flies by you and the wind comes rushing by. It's trying to fill the hole that the 18-wheeler kind of punched in there. So because air behaves similar to water like a fluid, we have surfaces on our aircraft called airfoils, so those are designed to take advantage of this fact. And to talk about airfoils, I'll bring in Brendan.
So this is how an airfoil looks. It's a 2D cross section of the side profile of the wing. So this isn't the top-down view, this is the side profile. If I draw out the rest of the aircraft, it would look something like this. There we go. Here's the window, vertical stabilizer, elevator, and your propeller, like that. So you have the leading edge, which is the side closer to the propeller. Trailing edge is the side closer to the elevator. And then you have an imaginary line between it. And it's supposed to be a straight line. That's the chord line, which connects the leading edge to the trailing edge. And that's important for how understanding how lift is produced. Next we have camber, which is curvature of the airfoil. You have the upper camber, the lower camber, and then you have the mean camber line, which is the average curvature of our airfoil. Next, we will be discussing the 4 forces of flight. I'll pass it over to Ayden.
All right, the aircraft in flight experiences 4 forces. I'd ask the student at this point if they know what they are. They'll probably tell me at least a couple of them. We have lift, weight, thrust, and drag. Lift is the upward force that acts on an aircraft to sustain flight. It can act any number of directions, but weight opposes it, always points straight down towards the earth. Thrust propels the aircraft forward, drag drags the aircraft back. In unaccelerated flight, lift equals weight, thrust equals drag. If the aircraft's speeding up, obviously that's accelerated flight, so thrust might be greater than drag for a second, but straight and level on accelerated flight, equal, these are equal as well. I am going to go and talk about lift now. Let's erase this. Probably ask the student if they can give me a cursory definition for kind of how lift is produced, or like kind of what lift is. I'll say, yes, the upward force of that acts on an aircraft that sustains flight. I would then talk about relative wind. So relative wind is the airflow that flows opposite the direction of the aircraft's moving. So the airplane is cutting through the air. If it's going straight, then the air from the plane's perspective is going this way. So straight level flight, relative wind's kind of doing that. If the aircraft was like level and like sinking, for example, relative wind is like this because it's going forward, but it's also going down. So the air feels like it's going backwards, it's going up. It's always opposite the direction. The aircraft's climbing, that's what it's doing. So the angle of attack is the next thing we're going to be talking about. This is like the pitch of the aircraft. It's directly informed by the pitch. So it is the angle between the chord line and the relative wind. At 0 pitch, there's going to be a little bit of angle of attack for our aircraft because it produces a bit of lift already. Let's say there's a higher angle of attack. So this is like the aircraft's pitch up a little bit. So this pitches up. Say the relative wind stays the same because the aircraft's still just going this way, but just like that. Higher angle of attack means a higher production of lift. This will continue until the aircraft reaches a critical angle of attack. At this point, the airfoil is creating as much lift as it possibly can. And anything past that means that there is insufficient air getting over the top. We'll talk about that in a second. There's insufficient lift production being done, and the aircraft no longer produces enough to stay up, and the aircraft will sink/stall. Okay, so air, like we mentioned earlier, behaves like a fluid. And a guy called Bernoulli had a theory or had a principle about how fluids behave, especially when they're sped up. So Bernoulli's principle. No, I'm not going to say principle. As velocity increases, pressure decreases. So I'll give you the old airfoil again. The airfoil is shaped in such a way that it creates a high velocity of air up top and a relatively lower velocity of air down below. How it does this is by displacing more air above the airfoil than below the airfoil. This shape of this airfoil means that there's more air gone up top here. So to fill that space that your hand leaves in the pool, that your airfoil leaves in the air, it's going to pull this air down into that. Pulling the air down like this. And what that does, the air is accelerated downwards. When it's accelerated downwards, the velocity increases. And we get low pressure. Conversely, we get a high pressure zone below the wing because this velocity hasn't changed. So relatively higher pressure, relatively lower velocity. So the other way around. Relatively higher velocity, lower pressure. The high pressure down here wants to get up to the low pressure because high pressure goes to low pressure. To equal that out, it pushes through the wing and it gives the wing an upward force because you can't go through the wing, so it's gonna push it up. The other theory of lift that we have is Newton's third law. When this air comes down over the end of the wing, this air that's going down meets this air that's going straight, deflects everything down because they collide and push down. So what's happening here is that the wing is exerting this downward force by interrupting it and pushing it down at the end there. So this downward force needs to be met with an upward force because Newton's third law says for every action there's an equal and opposite reaction. What's the equal and opposite reaction? It's the reaction of the wing being felt by the air upwards, lift. So that's how those two are produced. I'll hand it over to Brendan to talk about weight.
So at this point, I would ask the student, what do you think weight is? I'm sure they'd give me an answer that's pretty accurate. So weight is the force on an object downward towards the center of the Earth's mass due to gravity. Since the Earth is the biggest object around us, that's going to have the biggest influence. So if I draw an aircraft here, this is the back side of an aircraft or the front, doesn't matter, with the wings on top. Well, let's say an aircraft were to weigh 2,000 pounds. That means that the Earth is pulling down on that aircraft with a force of 2,000 pounds. Now, in order to maintain level flight, 2,000 pounds of lift will be required in order to do that. I'll actually erase that for right now, but these vectors are drawn to be the same on purpose. So future reference, if I draw a vector, just know they're drawn to scale. Now, where things get a little bit tricky is with something called load factor. So with load factor, weight doesn't change, weight is constant, but it feels like you weigh more. So what I mean by that is load factor is the ratio of total lift to total weight, and that gives you a G, which is a G-force. G-force is it's a force that is opposite the direction of your acceleration. So if you're flying in an aircraft, or imagine this is a roller coaster cart, if you're flying down and then you quickly pitch up, or the roller coaster quickly brings you up, your body still wants to go down, but the aircraft is now going up. And what that means is you're gonna feel all that extra force, like a G-force. If you've been on a roller coaster before, you know what I mean. So, how does this apply to aviation? You have load factor. When you enter a bank turn, your weight is still constant. You're still gonna be at 2,000 pounds here. And your total lift is similar to your vertical lift here, but now this total lift is divided into a vertical component of lift and a horizontal component of lift. And now, when you turn, your vertical component is actually less than your weight. So what's gonna happen? You're gonna start sinking, you start losing altitude. So what we need to do is we need to increase our lift production, our total lift, in order to increase our vertical component of lift and our horizontal component of lift like this. If you increase your total lift, you'll get enough force here to lift you up to overcome your weight and maintain altitude. That is load factor, and now we'll get into thrust here. So just like Ayden said before, an airfoil it is designed in order to utilize relative wind to create lift. And propellers have airfoils just like a wing has an airfoil, except instead of creating lift in the upward direction, it creates that same thing, lift, in the forward direction. That's what propels the aircraft forward. So I'm not going to go into all that since we already discussed it, but now I'm going to bring something called turning tendencies. So there's 4 types. You have spiraling slipstream. I'm just going to write down the first letter to save some time. Spiraling slipstream. You have torque effect. You have gyroscopic precession. And you have P factor. Those are the 4 types of turning tendency. So what I'm trying to say here is your aircraft will turn, it'll bank and yaw without any pilot control input. It'll do it on its own, and that's a byproduct of thrust being created. So there's 4 types, spiraling slipstream, I'll get into that. So what happens is the propeller's turning, it's turning clockwise like this here, turning clockwise, and that's creating a backwash of air that goes around the plane's body. It'll hit the left side of the vertical stabilizer, and that will cause the aircraft to yaw to the left. The tail goes to the right because it's being hit there, yaw to the left. That's all that happens for spiraling slipstream. Now, for torque effect, what happens is this aircraft, it is spinning clockwise like this, right? The propeller's spinning clockwise. There we go, just want to make sure you guys can see it. So it's spinning clockwise. All the internal engine components are spinning clockwise as well. And Newton's third law, as we just discussed, for every action or every force, there's an equal and opposite force, right? So if we're creating a force that is like this, that means that the internal engine components are turning that way. The aircraft's actually going to have an equal and opposite force to roll that way. So it's going to be rolling to the left as well. Next, we have gyroscopic precession. So I'm going to use this as the propeller now, since that's a little small and hard to see. But gyroscopic precession, there's 2 principles to a gyroscope. There is rigidity in space, and there's gyroscopic precession. I would ask a student, have you ever spun a top before? They would probably say yes, and I'll say, great. As it's spinning fast, it seems to be rigid in its location, but then as it loses speed, it'll kind of wobble and then fall apart. That's rigidity in space. We need to go over that right now. Gyroscopic precession, though, if you apply a force to a gyroscope, that force will be felt 90 degrees ahead on the same axis of its direction of rotation. That's where it'll be felt. So you apply it one place and it'll be felt 90 degrees later. So if you are in a climb here, this is your propeller, it's spinning, it's spinning, it's spinning, and I'm gonna freeze it right here. If you're in a climb, then you will apply a force to this part of the propeller, right? And your propeller spins 90 degrees later. That force is felt now, and that's going to be causing the aircraft to now yaw to the right. So that is gyroscopic precession. The same thing happens in a descent, but it's just the other way. So that's that. Now we'll get into the next one, which is P factor. I'm actually going to draw this one out because I think it's a little easier to visualize. So let me erase this here. So you have your descending blade and your ascending blade. And you have level flight, and you have flight at a high angle of attack. So every propeller is, or at least our propeller, is one long piece of forged aluminum alloy. It's twisted and it has 2 blades, a descending blade right here and an ascending blade right here. That's how it is. So just so you guys know, that's what that is. Now, I'm going to be showing you the side profile view of each of these. At a high angle of attack, your flight attitude is going to look something like this. That might be a bit extreme, but just so you guys get that. So, what do we have here? Now, your descending blade is going to look something like this, whereas your ascending blade is going to look something like that right there. Okay? At a high angle of attack, your descending blade is going to look something like this. and your ascending blade is going to look something like this. Okay, let me grab a second color so you guys notice. You guys remember where chord line is? I asked them that, they tell me, yeah, it's the line that connects the leading edge to the trailing edge of an airfoil. This is the side profile view. So the chord line is, I'm going to extend it out so you guys can see what I'm trying to visualize here in a second. Chord line is like this, and like
Brendan, draw it bolder.
Draw it bolder?
That's kind of
Okay, gotcha. Yeah, I'll draw it nice and bold so you can see it.
Yeah, there you go. Sweet.
Okay, so this is the chord line extended out so you can see what I'm trying to say. Now I'm going to draw the relative wind. So descending blade descends this way. That means the relative wind is felt this way. The ascending blade spins that way, so the relative wind is going to be felt like that. Right? Now over here, the descending blade is going this way. Relative wind is going to be felt like that. Whereas the ascending blade over here is going this way. The relative wind is going to be felt like this. These angles are relatively equal. That shows you that the same amount of thrust is being produced in level flight for both the descending and the ascending blade. At a high angle of attack though, these angles here are different. So as Ayden said before, when it comes to lift production, at higher angles of attack, you'll create more lift. Same thing is true for the propellers, airfoils. At a higher angle of attack, you'll create more thrust. So, more thrust is created on that descending blade at higher angles of attack, which means you're spinning. And on the right side, it's going to create more thrust. It's going to push the aircraft, and that way it's going to yaw to the left. So those are the turning tendencies. Now I'll pass it over to Ayden to discuss drag.
All right. At this point in the lesson, I would ask the student not how well they understand drag, more so like what they could think of that would prevent the aircraft from being able to go as fast as it possibly could through the air. They would give me something along the lines of form drag, probably. Skin friction, interference, not a huge deal if they don't know that. But I would say the drag is the backwards force on an aircraft that resists the movement of an aircraft through the air. There's two types of drag. There's induced drag and there's parasite drag. Induced drag increases with lift production and parasite drag increases with airspeed. I'd show them this graph that I then pull up where you can see the increase in airspeed and like along this axis and the drag along this axis. Parasite drag, low airspeed, low parasite drag. And as it increases, parasite drag increases. As airspeed increases, induced drag decreases because the faster you go, the less lift you have to produce, like angle of attack wise. Because this is very well seen. Past this, I also probably explain what like the point of best glide is. We don't have time to get into that. But below, down in the low airspeeds, the aircraft's going slow enough that you need to produce a lot more lift and a lot more like angle of attack to keep the aircraft level. More lift, more induced drag. And that goes and goes and goes until we're at such a high angle attack that the aircraft stalls. So, this is mine. We have two types of drag. We have induced, and parasite. Okay, I'll start with parasite because that's a little easier to understand. First one's form drag. That's anything on the aircraft body that sticks out, is kind of in the way, doesn't cut cleanly through the air. You're driving along the road, you stick your hand out the window, hand pushes back. That's literally physically your hand is just in the way and it's being felt, it's being pushed back by the air slowing it down. That's the form drag of the aircraft. That's the most basic, most easy to understand type. Next up, we got skin friction drag. I'd probably write out the whole thing. We don't have that much time. This is more microscopic. This is like the actual like surface and texture of the aircraft body itself pushing through the air that provides friction. Like, this is not the greatest example because this board is super smooth, but if I were to run my hand along the board, I couldn't pull it back down as fast as I possibly could because there's going to be some friction there. So there's friction on the aircraft because of the surface is a little bit irregular. So it's not going to flow perfectly smooth through the air. Last one, interference drag. So let's draw a little aircraft here. This will be drag that occurs in tight corners where air masses both meet up and one of them has to slow down because they both can't occupy the same space at the same time. So one of them has to slow down, and that slowdown of air is what generates drag. Basically, let's say these air masses are on a highway, like this, like one air mass coming this way through like this spot, the other air mass is on the merge lane coming around the outside, and they're both trying to meet the same spot. They can't. One of them has to slow down. Like I said, slowdown of air causes the drag. What we do is our aircraft come with speed fairings for those corners. There's like a little rounded piece that we add in there to make it so it's not a small point that the air has to go to. It's a much wider merge lane. So less of the air has to slow down because it can kind of merge together in that sense. Okay, then we have induced drag. Induced drag increases with lift production. So you got your aircraft here. This is like the back view of the aircraft. Okay, when lift is produced, obviously you got like the downwash over the aircraft of the wind, like the wind is going over the wings. That's what's kind of helping to generate the lift. And we got the low pressure on top and the high pressure on the bottom. And I'd ask the student, what does the high pressure want to do? They'd say, go to the low pressure. Cool. How's it going to do that? It can't go around the front. It's not fast enough. It can't go around the back. The aircraft's gone. Can't go through the wing. That just adds to the lift. So it goes around the side. It goes outward, upward, around each tip. But by the time it gets down to get to the low pressure, the aircraft's gone. So from the perspective of the aircraft, it just spirals out the back like this. But the issue is when it comes down when it comes out and down, it interferes with the downwash that's producing the lift, and it decreases the production of lift. So it's kind of ironic. The more lift you produce, the more wingtip vortices you produce. Therefore, the less lift you produce because it interferes a little bit more drag. So wingtip vortices create drag because they interfere with the downwash of the wing. On top of that, airfoil's right here. Wind coming down, we establish the relative wind kind of goes down that way. At the beginning of the airfoil, relative wind points this way. At the end of the airfoil, the relative wind points that way. Generalizing all the relative wind. Average relative wind direction is that-ish. And the relative wind is drawn, the lift vector acts perpendicular to the direction of the relative wind. So it's not going to act like this, it's really going to act like this. So there is that vertical component, but now there's a rearward component of lift. That adds that backwards force. The backwards force is the drag. And obviously as lift increases, that drag will increase as well. And last thing we really got to talk about is stability. I'll hand it over to Brendan to talk about that.
Thank you. So first thing I would do is I'd ask the student, what do you think of when you hear stability? I'd get an answer from them if they are close or not. It doesn't matter. I'll give them the definition. Aircraft stability describes how an aircraft responds to a disturbance from equilibrium. So there's two types. I'll draw them out here. You have static, which happens the immediate moment right after the disturbance happens. It's more of like an instantaneous thing rather than over time. Where you have dynamic on the other hand here, and that happens over time. How does the aircraft respond to this disturbance from equilibrium over time? And then there's three subtypes. There is positive, which I'll define in a minute here. There's neutral, and there's negative. And then same thing over here, positive, neutral, and negative. I'm going to draw out a basic aircraft here. Here's the body of the aircraft, the wings, and the horizontal stabilizer. Same thing over here. All these examples are going to be the aircraft flying from left to right. Here's the desired flight path, is straight and level. And for all these examples, I'm going to show a disturbance in the form of a wind gust at the same location with the same strength. So it will look something like this. There we go. So now you all can see desired flight paths, gust of wind, disturbance, There's a different color here. So, positive static stability describes an aircraft flying. It gets deflected and then it comes back to where it was before. It goes back to equilibrium. That happens the immediate moment right after it gets deflected off its course. Then you have neutral. It's flying. It gets gets deflected here, and it keeps that new deflection forever, like that. That line's supposed to be straight. And then you have negative. Aircraft is flying, and it gets deflected, and it just gets worse and worse and worse and worse and worse and worse, right? Those are the three types of static. Then you have positive dynamic. So this is more practical for the real world scenario. That does exist, but this is over time, so it's a little bit easier to visualize. Aircraft is flying, gets deflected, and then it will actually oscillate, and it'll get better and better and better until it's back at equilibrium. Then you have neutral. Aircraft is flying, it will oscillate, and it'll keep that same oscillation the whole way through because that deflection isn't changing and it isn't getting any better or any worse. Then you have negative lastly. Aircraft is flying, it gets deflected, and it will get worse and worse and worse over time. So then I'd ask the student, which one do you think is the best? Or I should say the safest. Training aircraft will have positive dynamic and typically positive static stability as well to keep you in a nose down position that's easier to recover from. Those are the three types. Now I'll go over the, let's see, so stability affects two areas. There's maneuverability and controllability. What maneuverability is, it describes the aircraft's ability to move easily and withstand stresses. And then you have, well, that's affected by many things like weight and size. Then you have controllability, which describes the quality of an aircraft's response to pilot control input. Those two are important, but for the sake of time, we're going to move on to the different types of stability. So I already spoke about longitudinal stability. You also have lateral and directional. So the same concepts apply, just on different axes. You have your lateral stability, which is like this. We already spoke about longitudinal, which is like this. And then you have directional, which is on the vertical axis, like this. And now I'll move it on to Ayden to discuss the conclusion.
All right. So today we talked about the four forces of flight: lift, weight, thrust, drag. Lift goes up, weight goes down, thrust goes forward, drag goes backwards. We talked about load factor. We talked about, you better not do that. We talked about load factor. We talked about the different turning tendencies. And we talked about the different types of drag and whatnot. We talked about the different types of stability as well. And this is really important to understand kind of how, the principles of flight kind of work and how your aircraft behaves in the air, because it's very important to have a real understanding of that instead of just knowing like, like what my stall speed is, like how do I do a turn? Because an understanding of load factor helps you perform a steep turn better because you need that back pressure. An understanding of like how lift is generated helps prevent you from doing a stall. Your performance will improve when you know how this stuff works and it's like second nature for you. An understanding of these things always makes you a better pilot. So that's been Brendan. I've been Ayden. Thanks for watching.